Welcome, everyone. Let's begin our exploration of how metals occur in nature. Imagine digging into the Earth's crust. You won't find metals lying around in neat blocks like in a jewelry store. Instead, they're scattered in different forms, free, combined, or even alloyed. Aluminium makes up nearly 8% of the crust, while iron contributes around 5%. Now, think of gold and platinum. They're too stubborn to react with oxygen or water, so they're found free in nature, shining in riverbeds as nuggets. But most metals are less fortunate, they're trapped in chemical compounds like oxides, sulfides, carbonates, and halides. Some even appear as natural alloys, for instance, electrum, which is a golden mix of gold and silver. Remember this, only a handful of metals are found free, the rest must be extracted from or locked tightly in rocks. Bauxite is the principal ore of aluminium, but it's never pure. It carries unwanted silica, iron oxides, and titanium dioxide. These impurities behave like stones mixed in rice, they must be removed before cooking. The ore is crushed and ground to liberate alumina minerals. Gravity and magnetic separation help reduce the iron-rich parts. To handle silica, we sometimes use caustic washing so that troublesome sodium aluminosilicate gels don't form later. By cleaning up at this stage, we save expensive chemicals downstream and reduce the volume of red mud waste. This is why metallurgists say better feed, better yield. Now comes the chemical cooking. In the bare process, bauxite is digested with hot sodium hydroxide under pressure. The alumina dissolves as sodium aluminate while iron oxide and titanium oxide remain as red mud. The reaction is Al₂O₃ plus to NaOH gives to Al₂O plus X plus 1 HO. After digestion, the slurry is clarified, the red mud is settled or filtered off. The clear sodium aluminate solution moves forward. Controlling silica is important here because otherwise insoluble scales line the pipes and vessels. Temperature and pressure matter too. Gibbsite dissolves more easily than boehmite or diaspore. That's why the mineral form of bauxite influences energy use in digestion. Once dissolved, alumina must be brought back out, this time in a purified form. We cool and dilute the sodium aluminate solution and seed it with fine aluminium hydroxide crystals. The reaction is Al₂O plus 2HO gives Al₄O plus NaOH. Alternatively, with carbon dioxide bubbling, Al₂O plus 3HO plus CO gives to Al₄O plus NaCO. The aluminium hydroxide precipitate is then washed and calcined at high temperature. The reaction is 2Al₄O on heating gives Al₄O plus 3HO. This calcined alumina is white, porous, and ready for electrolysis. Think of this step like crystallizing and drying sugar. We now have a stable, transportable feed for the next big transformation. Now comes the heart of aluminium production, the whole Héroult electrolytic cell. Here, alumina is dissolved in molten cryolite, NaLF, often with calcium fluoride added, at about 950 degrees Celsius. The cryolite lowers the melting point and improves conductivity. At the carbon cathode, aluminium ions are reduced, Al₃ plus 3 electrons gives aluminium liquid. At the carbon anode, oxygen ions react with carbon, 2₂ plus C gives CO plus 4 electrons. Overall, the process is 2Al plus 3C gives 4Al plus 3Co. Fresh alumina is fed continuously to maintain about 2 to 4% concentration in the bath. If it drops too low, anode effects occur, releasing harmful gases like perfluorocarbons. This is why operators monitor and feed alumina carefully. Running a whole Héroult cell is as much art as it is science. Ideally, the voltage needed is about 2 volts, but in practice cells run at 3.8 to 4.5 volts due to heat losses, resistance, and side reactions. Energy consumption is around 12 to 15 kilowatt hours per kilogram of aluminium produced. That's why aluminium is sometimes called solid electricity. The purity of the metal is generally very high, but traces of sodium, calcium, or iron can sneak in. Skimming draws, careful tapping, and refining control this. Environmental care is crucial. Fluoride gases are captured by passing fumes through alumina, which absorbs them. Preventing the anode effect reduces greenhouse emissions. Stability of feed and bath chemistry improves current efficiency and reduces costs. Let's work through a real calculation. Suppose we want to produce 100 kilograms of aluminium using a cell running at 50 kiloohms and 4 volts with 92% current efficiency. Step 1. Moles of aluminium is equal to 100 divided by 27, about 370 moles. Each mole of aluminium needs 3 moles of electrons, so total electrons is equal to 1110 moles. Step 2. Charge required is equal to NF is equal to 1110 times 96,485 1.07 times 10 coulombs. Adjusting for 92% efficiency, corrected charge is equal to 1.17 times 10 coulombs. Step 3. Time is equal to Q divided by I is equal to 1.17 times 10 divided by 50,023 30 seconds, or about 39 minutes. Step 4. Energy is equal to Q times V is equal to 1.17 times 10 times 4.66 times 10 joules, which is about 129 kilowatt hours. This shows why aluminium is energy hungry and why recycling aluminium saves up to 95% of energy compared to primary production. Always remember to factor in efficiency when doing these calculations.